Imagine cutting a 7-hour flight into just 3 hours, no more long, grueling jet lag or endless airport waits. Supersonic and hypersonic planes aren't just science fiction, they're almost here, promising to revolutionize how we travel and defend our nations. Ready to fly at the speed of sound? Strap in, because aviation is about to break the sound barrier once again. Why supersonic and hypersonic aircraft matter. Supersonic and hypersonic aircraft are gaining significant attention in the aviation world, marking a transformative leap in both commercial and military flight. Supersonic flight refers to aircraft that exceed the speed of sound, Mach 1, while hypersonic aircraft travel at speeds greater than Mach 5. These aircraft promise to dramatically shorten travel times, offering potential breakthroughs in both civilian air travel and military defense. While supersonic speeds have been achieved before, notably with the Concorde, hypersonic speeds, over 5 times the speed of sound, are still in the experimental phase. With technological advancements in aerodynamics, propulsion systems, and materials, both forms of flight are now closer than ever to becoming a mainstream reality. The commercial viability of supersonic airliners and the military applications of hypersonic missiles have led to significant investments in these high-speed flight technologies, promising a new era of aviation that could reshape how we travel, trade, and defend. What's the difference between supersonic and hypersonic aircraft? At the core of the supersonic and hypersonic revolution lies the difference in speed. Supersonic aircraft travel faster than the speed of sound, Mach 1, typically between Mach 1.2 to Mach 2.5, which allows them to cut travel times in half compared to conventional subsonic aircraft. For example, a flight from New York to London, which typically takes 7 to 8 hours, can be completed in just over 3 hours in a supersonic aircraft. On the other hand, hypersonic flight refers to speeds greater than Mach 5, reaching speeds that are more than 5 times the speed of sound, around 6,174 kilometers per hour or 3,836 miles per hour. Hypersonic technology presents entirely new challenges due to the extreme heat and pressure generated by air friction at such high speeds. While supersonic planes, like the Boom Overture, expected to fly at Mach 2.2, are closer to commercialization, hypersonic aircraft are still in the developmental and testing phase. Scramjets, which are key to achieving hypersonic speeds, function by allowing air to flow through them at supersonic speeds without mechanical compressors. They promise to revolutionize both travel and warfare by drastically cutting travel times and enhancing defense capabilities. A glimpse into aviation's past, supersonic and hypersonic dreams. The dream of flying faster than sound dates back over a century. In 1947, the Bell X-1, piloted by Chuck Yeager, became the first aircraft to break the sound barrier, marking the dawn of supersonic aviation. The Concorde, introduced in 1976, flew at Mach 2.04, making transatlantic travel faster and more glamorous, though it was retired in 2003 due to high costs, inefficiency, and environmental issues like sonic booms and a large carbon footprint. Hypersonic flight, developed primarily for military and space exploration, saw a milestone in the 1960s with NASA's X-15, which reached Mach 6.7. Today, companies like Boeing and Hermes, alongside NASA, are advancing both supersonic and hypersonic technologies, building on these historical achievements to push aviation into the future. What's driving the supersonic and hypersonic revolution? The drive behind the supersonic and hypersonic revolution is fueled by the demand for faster global travel. Supersonic jets could cut flight times in half, New York to London in just 3 hours, and transcontinental flights in 4 to 5 hours. This speed boost would enhance business productivity, allowing executives to achieve more in less time. On the military front, hypersonic flight at Mach 5 Plus offers new strike capabilities, reconnaissance, and missile defense advantages, bypassing current systems with speed and maneuverability. Advancements in aerospace materials, fuel efficiency, and computer modeling are making these high-speed technologies more feasible than ever. As a result, supersonic and hypersonic flight represent the next major leap in aviation, promising both commercial and military breakthroughs. How do supersonic and hypersonic aircraft work? Supersonic and hypersonic aircraft rely on advanced propulsion and aerodynamic systems that differ from traditional subsonic planes. Supersonic jets use turbofan engines optimized for high speeds and fuel efficiency at cruising altitudes. To minimize the sonic boom, engineers design specialized nose shapes and wings, with models like NASA's X-59 focusing on quiet flight. Hypersonic aircraft, however, use scramjet engines, which operate without moving parts like compressors, allowing air to flow through the engine at supersonic speeds. The key challenge for hypersonic flight is the extreme heat generated by air friction at speeds above Mach 5. To withstand this, hypersonic vehicles use heat-resistant materials like carbon-carbon composites and specialized alloys, with thermal protection systems essential to prevent disintegration at high speeds. Key players in the race to hypersonic flight. The race to hypersonic flight is being led by both government organizations and private companies. NASA, in partnership with Lockheed Martin, is developing the X-59 Quest, a supersonic aircraft aimed at reducing sonic booms while reaching Mach 1.4. Boeing is involved in both military and civilian projects, including the X-51 Wave Rider, which achieved Mach 5, and research into advanced scramjet technology. On the commercial side, Boom Supersonic is developing the Overture jet, capable of Mach 2.2, with flights planned for 2029. Startups like Hermes are targeting Mach 5 speeds for hypersonic airliners, with flights expected by the mid-2030s. Virgin Galactic, led by Richard Branson, is investing in suborbital space travel, laying the foundation for future high-speed technologies. The benefits of supersonic and hypersonic travel. Supersonic and hypersonic travel offer benefits that go beyond just speed. First, they enhance global connectivity, reducing travel times significantly. Business travelers can attend meetings in multiple cities in a single day, while tourists gain more time at destinations. Hypersonic flight also has military advantages, enabling rapid global strikes, faster response times, and advanced surveillance capabilities. On the commercial side, faster air travel boosts industries like tourism, trade, and international business, driving economic growth. Additionally, advances in sustainable and fuel-efficient supersonic technologies promise to make air travel more environmentally friendly, supporting the goal of net zero aviation. Environmental challenges and innovations in supersonic and hypersonic flight. Supersonic and hypersonic flight bring exciting benefits, but also significant environmental challenges. The primary issue with supersonic flight is the sonic boom, which can disrupt people on the ground. New designs, like NASA's X-59 Quest, aim to reduce this impact. Another concern is the carbon emissions from high-speed jets. The industry is addressing this by developing sustainable aviation fuels made from renewable sources to lower the carbon footprint. Hypersonic flight faces its own challenges, especially with the extreme heat generated at Mach 5+. Engineers are exploring heat-resistant materials and fuel-efficient engines to make hypersonic travel more environmentally sustainable. Challenges in achieving hypersonic travel. The leap from supersonic to hypersonic travel presents significant technological and engineering hurdles. One of the biggest challenges is the heat generation at hypersonic speeds. As aircraft move through the atmosphere at Mach 5, the friction between the air and the aircraft's surface generates massive amounts of heat, often in excess of 1,500 degrees Celsius, 2,732 degrees Fahrenheit. Materials must be developed that can withstand these temperatures without melting or deforming. The development of scramjets, engines that allow an aircraft to travel at Mach 5 and higher, presents further challenges related to airflow and fuel combustion at such high speeds. Finally, control and maneuverability are also key issues. Once an aircraft reaches hypersonic speeds, keeping it on course and maintaining stability becomes much more difficult due to the extreme forces at play. That's all for today's video. If you're as excited about the future of high-speed aviation as we are, don't forget to hit that like button and subscribe for more mind-blowing updates. Stay tuned for all things supersonic, hypersonic, and beyond. Let's take flight into the future. See you in the skies.